So it's really interesting. This is really working well, and we'll see how things progress on that. So first thing I'm going to do is I'm going to switch over to the oscilloscope to show you just the difference between an inductor and a capacitive circuit. So both of these have just give you an idea, these both have a 220 ohm resistor. My capacitor is a 154. Let me actually give you the number. It's a 0.15 microfarad capacitor. I had to calculate that out. And my inductor is going to be a 10 milliamp. So I'm going to do a switch between it, but it's really easy to switch. But I want you to pay attention to is the difference between an inductor and a capacitor. You're going to see this, and it's important when we get to RLC circuits, which is coming up very shortly here. So first circuit I'm going to show you is the capacitor, and the second is inductor. First thing to remember is that the capacitor lags behind the voltage total. Inductor is going to lead, so you're going to see that on the scope. I only have a 2-channel scope, so I'll have to switch between the two. But watch the blue line. The key is the blue line. So first thing I'm going to do is switch you over. Okay, so here's the circuit. So I got my function generator coming in here. So I got my function generator coming in. So this is the channel 1. This is channel 1. And this is channel 2. And I'm going to show you on the scope what it looks like. Okay. As you can see on the scope, our capacitor is leading our voltage on here. Everybody sees that, right? So if I switch, I said lagging, sorry, lagging behind. And if I switch over to my inductor, which we're going to study today, you notice that the voltage on the inductor leads the source voltage. See the difference between the two? Let me do that again. So this is, drop this one back down. So this one's lagging behind source voltage, and this one is leading. And if I'm stretching over, it's because I got all the equipment in front of me back there. So does everybody see the difference between the two? It's pretty good. It's an important concept to understand, because as we get into RLC circuits, which is the next one, bridging these two concepts together is going to be important. So I'm going to do is switch back, and we're going to do is go to that series circuit, the first one. I think it's not number 2. It's called RL circuit or something like that in your PDF. So pull that one open, and we're going to go back to that, and we're going to use multisim on this, and then we're going to build the circuit and test everything. So we're going to do it on multisim, and you guys are going to do it whatever you have on your side. We're going to come up with some answers, and then we're going to switch back over to build the circuit itself. Second part of this is we're going to take 2 inductors, and we're going to build the circuit with 2 inductors, and then we're going to use the math function on the function generator to actually get the voltages across and do some of the fun stuff with this oscilloscope. Okay. All right. Good. We got a lot of people coming in today. Okay, the first thing I'm going to do is the circuit that you're going to pull up, and I'll give you the name of it right now. It is going to be called If you pull it up on the PDF, it's called RL circuit analysis. It should be RL circuit analysis, and it should look like thank you, Drake. It should look like I'll get it up there in a second. I'll pull it up. Not that one. Definitely not that one. I had to open it up. There we go. It should look like this on your PDF. So I'm going to go ahead and bring this up, and we're going to do some math on here. Got to get rid of some of this stuff. I know there's a lot of information that you have on yours that is that's incorrect. So I just want to make sure that we're going to get the correct answers. I set this up so we have a 10 volts RMS, 1.5K hertz. My goal here is to get an X-of-L, my inductive reactance, as close as I can to the 100. There's a reason for that. I just don't want all the voltage dropping across that L1. So,
hey, Charles.
Yes.
Are we writing these answers down and turning them in eventually?
Yeah, you're going to turn them in. Yes, you can. Or you could do is, as long as you're participating today, and you show me the participation, I would not have a problem with that. But I just want to make sure. I think I like the idea of everybody turning things in. And I'm giving everybody credit for that, like we did the last couple days, right?
Yep.
Okay, I have to add that to the 103. Basically, what I've been doing is for the last few nights is putting together like a Word document where everybody's participating and then filling in. This is a little different class. That's where the PDFs coming in, so you can write things down on paper and then submit it to me. So I get doing work. And the nice thing about that, I give you credit for it. It's a homework credit. I might even go up to. I might even make a lecture lab on the lab portion of the grade. So we'll see. We'll talk to each other about that. So first thing I want you to do is find X-of-L1 using the information you have there. So everybody find X-of-L1, and I'm going to go ahead and let's get the chat back up. Chat was up. Where is it at? I missed the chat. Chat's gone. My chat is missing. Somebody type something in for the chat, just FYI to me, so I could do it. Just somebody put something in, because I'm hitting chat and it's not allowing me to come up with chat. There we go, it's back. Thank you, Jeff. I don't know where it went. It just kind of disappeared on me. I was like, well, this thing's been going. Okay, there we go. All right, X-of-L1. Everybody, you can put it in the chat or you can speak it out loud. Tell me what you get for X-of-L1 using information that's on the screen right there. Does everybody have the PDF? Everybody go to the email to get the PDF? Daniel, did you get that?
Yeah.
Okay, John, you got it. Daniel, did you get it? Okay, if there's anybody who's not...
I got it, but I don't have it open. You want me to open it up, or? You
can. Yeah, that's fine. As long as you're writing the stuff down, just have it in front of you. It's just a reference to you, because I know that you can't. Some of you cannot print on your screens, so it's just a reference. So if you want to, you can have that as a reference. But make sure you're writing down, submitting the stuff to me today. Okay?
Is this the first or second PDF that you sent us?
This is going to be the first. It should be called circuit analysis, or circuit analysis.
I think that's what this is a lab. This is
a lecture lab. I'm combining a lot of stuff. I'm combining a lot of stuff here just to so we participation. So everybody, Exabel 1. What'd you get for Exabel?
I got 94 ohms.
Okay, 94. Thank you,
Oh,
Daniel.
that's right.
That is correct so far. Let's find out. Let's see what the class says. What'd you get, Jeff?
So I got 94.248
That's good. Okay, going out a little bit helps out.
kilo
Yep,
ohms. Kilo ohms.
kilo ohms.
Yeah, because your circuit specifies 1500 kilohertz.
Whoa. Yep, I see that.
So-
Guess what? Can you knock that off? 1500.
Yeah.
Yep.
Okay, then it's 94 ohms.
94 ohms. Thanks. Actually, let me take care of that mouse. Let me take care of that value right now. $15. It was changed on my end. Now it's changed. I just changed it for you. There you go, 1500 ohms. All right, 94. Thank you. Sorry about that. That makes a big difference, doesn't it? It makes a huge difference. If we go from a circuit where there's nothing, no drop across the resistor, to everything be dropped across the inductor. That's not always what you want when you design a circuit. A lot of times you want to do is try to get the inductor to have a little bit of voltage across it, because remember, if you put a lot of voltage across that inductor and you shut down the circuit, it's going to go way up on it. So just FYI too on it. All right, 94.28 ohms. Let me get the ohms on there for you guys. Okay, it's good. Let's do that. Okay. All right, so on this, we know that if we look at just a diagram on this, I'm trying to, yeah, I'll work with that. All right, so we have, let's call this the voltage of the inductor, and let's call this, what is this, current? Yeah. So basically we have a circuit that looks like, remember the other way was with the capacitor, it was the other direction, right? So this is going positive. The inductor's going positive. Capacitor VC is actually going, excuse me, is going toward the negative end. So it's pointing downward. So this one, we're actually forcing it upward, which makes some sense. So if we look at this, and we're going to do some trigonometry on here in a second. So this is where the right triangle comes in. Again, we have the right triangle. And then, so this is going to be 90 degrees. This is going to be, the voltage of the inductor is going to be leading the current. It's going to be leading the current. In the other one, the voltage across the capacitor was lagging behind the current. Okay, so keep that in mind. Race. There we go. Let's go. I'm just running out of room here, so I'm just going to erase some stuff here. All right, so if we actually want to find out and I'm going to put this up here so you can see this. All right. Does resistors have any phase angle? Nope. So where does that go? Bottom or on this side? Somebody tell me. John, where does R go? On the bottom here or on the side?
Bottom.
Yep, it goes on the bottom. And that tells us there is no phase. There's not going to be any phase angle. There's not going to be no phase angle. What's over here?
L1.
So we're going to call this x sub L1. Yep, x sub L1, because we're in ohms. Remember, we want to keep an ohms on this thing. So x sub L1. Okay, and let's get this finally. Just do this. What's this called? If we're in AC circuits, what's this called?
Z? ZT?
Yep. Z total. What's Z called?
Resonance impedance?
It's impedance, total impedance, right? This is your total impedance, right? So to find the total impedance, because if this is 90 degrees right here, and this is our theta right here, we want to know what the phase angle difference between these two are, okay? Because we use the arctangent of it, and this time the arctangent is going to be a positive number instead of, it's not going to be negative because this x sub L is pointing upward. So if that's the case, this is 90. Here's our phase angle. So Z total is going to be equal to the square root. And the question is, why are we using the square root? What's the reason for that?
Because of the Pythagorean theorem?
Okay, we have the Pythagorean theorem. Okay, but more importantly, what is going on with that, Brett? Why do we have to use trigonomic functions?
Is it because the AC signal, there's a phase difference?
There's an AC signal right there. Yep, there's an AC signal. Anytime you have an AC signal, because we're dealing with some sort of degree, right? We're using degrees on here. First of all, we know that an AC signal, if we draw that out, so if I draw this out, and I'm going to use degrees on here. So basically we have 0, 90, 180, 270, and 360, or if we go on pi's, that's pi, and there's 2 pi right there, right? That means we have some sort of trigonomic function going on here. So we just can't use the standard analysis of using like R1 plus x sub L1. It doesn't work. So in this case, we're going to have to do is use the Pythagorean theorem. So what we do is r squared plus x sub L squared is equal to z squared. And if we square root the whole thing, we just get z squared. Z is equal to the radical of r squared plus x sub L squared. So give me z total on here, please.
137?
All right, we got 137. Daniel, Jeff, what'd you get? You can type in Jeff if you don't want to speak.
Still working on it.
Okay. Everybody go ahead and just either put on the chat or just let me know. I'm going to check my stuff too. And go out 3 decimal places on it.
They're at 137.414.
I also got 137.381.
Did everybody go out with 3 decimal places on your x sub L?
Yes, we did.
I didn't when I did the math, but I'll redo it.
Okay. So if you get anywhere between 137.244 or 414, that's fine. So anywhere in there, anywhere of these, like I think Jeff, you got 0.244. Is that correct? Yes. So that's legitimate. Off on your math. But we're talking. What are we talking? the difference between the two. It wouldn't really affect your answer very much. So you would come in really in the ballpark on it. But if we were making something, let's say we were designing a filter circuit, we want to make sure that we go out longer on the decimals. Because when I was in engineering, when I was going through my engineering classes, we would have to go out like 5 or 6 places just to get this thing almost accurate. We did it with only 2 decimal places, and then we went a way out. I remember this still. And we designed a circuit. One circuit didn't work, the other one worked. That's how engineering works. But I know you're not engineers, but I'm just saying that's how we were taught to do it. Okay, so when we were working with, as we were building up to our classes and doing all, getting it ready for our degree, we were always told go out many places. For as a tech, as long as you get close, you're fine. But if you're working with an engineer, you're working in a group with these guys or with these people, remember they're always going to go out a little longer in decimals. Or they may use some strange little squiggly lines called calculus. So there's 2 ways to actually get the answer. So calculus, which would give you almost a perfect answer, a real world answer. So, all right, 137.414 is good. Okay, so we have Exabel, we got Z total. Let's do I total. So I total. Somebody give me the equation for I total.
Square root of I squared R plus I squared L.
Okay, looks like you're in parallel. Something simpler. Would this work?
Yeah.
Drake, what'd you get for this answer if we take this guy right here?
One moment.
It's fine.
I got a 72 milliamps.
Milliamps, okay. Does the group agree? Give me a thumbs up or give me a thumbs
Yes.
down. Yes? Okay, got a thumbs up. Okay. All right. So you got 72.77 mil, is that correct? Whoa.
Yes.
All right, I'm gonna get rid of my triangle here because I need some space.
Yeah, you got that.
Good. Thank you, sir. Okay. I'll put my triangle back up in a second. So is current the same throughout series circuit? I think it is. What do you think?
Wait, what?
Is current the same throughout a series circuit? I'm asking. I think everybody's
What's the question?
is current the same throughout a series circuit?
Yeah.
It is. Yes, it is. I'm just getting rid of some stuff here. Okay, so let's go find. Let's do both. Let's find VR1, and let's find VXabel. Now, technically, I don't have to use Ohm's law. I can use the voltage divider rule at this point too, right? I could use the voltage divider rule and come up with it, but one way to the other works, right? So if I take Ohm's law and I take I total times it by R1, and let's get VXabel. There's VXabel. Get off there. And I'm just going to use the I total since we calculated it already. All right. Let's just somebody find VR1 for me. That's the voltage across here, and then VXabel 1 over VXabel. Let's keep the 1 here.
So couldn't we just subtract VR1 from 10?
No. Remember, you're doing trigonometry. You're using trigonometry. We'll talk about that in a second here, too. Good question.
All right.
Good question. I'll get to that in a second. If we did, I want you to go ahead and try it, but I know it's not going to work. And then I'm going to show you a reason why. Okay?
VR1, I had 72,000. No, 7,000.
72,000?
No, 7,000. I mean 7,000.
7,000? Sounds like you're a little off there. Just a little bit.
Yes.
Just sounds like your decimals off. Yes, go ahead.
I got 7.22 or 7.277 volts.
Okay, 7.27. Daniel, it sounds like you accidentally entered in -6 or something in there. That's what it
Yeah.
sounds like. Sounds
I'm
like
already
it.
good.
Yeah. Just watch those decimals. You notice that he got. First of all, he realized that he had a problem. I'm gonna let you know he realized it. He's like, wait a second, I only at 10 volts. I'm getting 7,000. That's the first indicator that you're probably something you added into your engineering notation was off. And the second thing is like, that's not right on my test. So just keep an eye on those things. If you're ever getting more voltage out than you have in, this is not fusion, okay? So just keep that in mind. Unless you shut down the circuit and you got a quick amount of voltage coming off that inductor, but no. Okay, and let's do VX about 1. Remember, we're in mils here, so that is 72.77. Let me just put that down for him. And then times it by R1. So X bell. Okay. Did anybody else come on? Nope. Okay. This is great because you guys are doing great right now. Participating, awesome. So what do we get for X about 1? Anybody?
I'm not sure.
Okay. So let's see. Let's just do this. 70. Let's go
6.858.
7. Yeah. What was that? What is it?
6.858.
There you go. Good. 72 mils. And then you multiply that by your 94.28. 248. Sorry. 248 volts. And that gives you 6. Was that you, Mr. Martinez, that gave me that answer?
Yes.
Excellent job. 6.85. And basically, I would round it up, but if you gave me an 8, that's fine. It could be a 9 or 8, that's fine, going throughout decimal places. So just FYI to you, watch out those, if it's 6 or above, round up the one on the left a little higher, but that's fine. It's not going to make a difference on your answer. So, John, you asked me, couldn't I take the R1 and subtract it from 10 volts and get it? Look what happens when you do that. 7.22 from 10 does not equal 6.8589. It does not. Here's the reason why. I'm running out of room here. Okay, let me put this, let me draw this up here for you. So this is VR, and this is VX about. And if I switch over to a red, this is V total. Here's theta. Here's 90 degrees, and here's theta. Do you see it, John, now?
Yeah, I'm just trying too hard.
No, that's a legitimate question. That is a legitimate question. Excellent. But if we take VR square it plus V Xabel square, which we get equal to V total. Let's check it. So go ahead and put in 7.277, square it, and then 6.859, square it, and then take the square root of those. So in fact, I'm out of room. I'm going to erase the I total down here so we could just get that. I'm just going to get rid of this guy. I'll put him back up here in a second. So if I take and I put in, so if I take VR1, and there's a square root here of it.
Why do they both come out to be like 7 volts?
Okay, good question. Take a look at your ohms on both of them. How close are they?
Really close.
Yeah, they're really close. There's the reason why I did this. That was the reason why I did that. So, yes, go ahead, sir.
So I guess another way of looking at it would be if I took the two voltages, the 7277 plus the 6858, and treated them as peaks, and then times it times 0.707, then I get back to my 10 volts RMS.
Yes, it is. Because it is the radical. Yes, that is correct. That should work too. Yeah. Because there are peaks. Those are peak voltages. Yes. Those are peak voltages. Absolutely. And we can show that on the scope here in a second. So, yep. And then you just take it and give it back to. So let's see. 7.277 squared plus 6. See how, look at your calculator. I got 10.0000305. Now you see why I went out decimals too on here, right? The decimal makes a big difference. Because if you didn't go out decimals, then you get 9 point something, 9.8, 9.9. So our math works, but we're not done yet. What do we have left? What do we have left?
Measure VO.
Phase
Right.
angles.
Phase angle, yes. I'm just writing down some stuff here for this. Let me get my eraser here. There we go. I'm just writing things down so we can see it. So we got 72.77. And this is an amp-meter, by the way. This is an amp-meter right here. And this is a voltmeter. Okay, a phase angle. And let me get rid of this guy. So if I could use any of these right triangles that I want. I could use VXabel over VR. I could use Xabel 1 over R. I could use anyone. I'm gonna use let's use this one. I'm gonna use this one right here. So I'm gonna use the theta is gonna be equal to the arctangent of Xabel 1 over R1. And I'm gonna do it the same way with the voltages to show you're gonna get the same phase angle. So if I do the arctangent, remember you have to be in degrees. By the way, if you were doing it in radians, you just have to let me know that you're doing it in radians. Just remember that if you do it on your calculator in radians, you have to show me pi's and all that on your work, on your quizzes and tests. Because I'll be like, what are you doing? Because I don't want to try to figure it out. I'd rather see your work and then compare it to, I'll redo the work myself and I'll compare it to say yes or no. So just keep in mind on that. So Xabel is 94.28248. And it's not negative because our arrow is pointing upward. Our vector is actually pointing upward over 100. So this gets be close to almost an arctangent of 1, which is close to 45 degrees. This goes out to be 43.3. So our phase angle is 43.3. Let me show you what that looks like. So do you agree with this?
Yes, I do. I got 43.30.
Yeah, 43 point. Whoops, you're right. I'm wrong. It was 30. You're absolutely right. I just re-looked at it. I was talking. And there's degrees. Okay, so let me write down some of my values here. So we got 6.859 volts. All right, I'm just racing things here so I could make some room so I can show you what this phase angle looks like. And all right, so we gotta get the phase angle. So this is X about 1. Here's R1, and here's theta. And this says we get about 43.3. Did everybody get about 43.303? Close to 45 degrees. There's another reason why I wanted it to be to 1 to 1, because if your voltages are close to it, it should be close to 45 degrees. So anytime you take a tangent of arctangent of 1, you get close to 45 degrees. Just throwing some math out there. All right, so let's see if we get, I actually want to see if we get this 43.03 using the voltages. So we're going to do the same equation. Instead of using X sub L, we're going to V X sub L1 over VR1. And you tell me what you get.
Wait, what did you say?
So we're going to take and use the voltages to find our phase angle. So we're going to take 6.859. I'm trying to read my handwriting there. 6.859 and 7.277. So we should get close to the same phase angle.
Yep.
Okay, one last thing we have to do is power. I want to know how much power we're actually pumping through this inductor right here. So what equation do we want to use? What equation? Jeff, what kind of equation do you want to use? What kind of equation do you want me to use for the class on that?
Trying to find it, hang on.
That's good. Take your time. I'm just getting things ready for it.
Well, would our P equals IE work in this case?
I times E. I would say so. I would say so. Let's do it. Let's see what happens. So we have I times E. And E is equal to V, by the way. So this V is actually an E right here. The reason we use between V and E is V is usually for DC voltages and E is for AC voltage. I've been keeping it everybody the same on that. Just keep an understanding on that. Okay, I times E. Go ahead, somebody tell me what you guys get on that.
Could we also use 1/2 times L times I squared?
1/2. The radical, the square root of, I think so. I think it's one of the equations. The radical of,
No, it's not the radical. It's just the hat, like 1/2 times L times I squared.
L times I squared. I'm not familiar with that one. I know I'm familiar with some radical that you have. I don't have the sheet in front of me.
Never mind, it says energy. It may not be power.
Power is energy.
Okay, well then yeah, it's in the book on
Okay,
page
so
611.
611. Just go ahead and use the I times E. But John, I'm going to take a look at your 611. You said, right?
That's correct.
Wait, what are we doing?
Power. So I times E. So X sub L 1. That's where we find the power. So I is 72.77 mils, times it by 6.859.
I total or I? Oh no, wait, never mind.
It's I total is I total throughout the circuit. We'll get back to you on that, John. I think you are correct on that. I remember. Okay, what'd you get for that one? For power?
Yes, just under half a watt,
Yes.
0.499.
Yep, 0.499. Actually, I'm just gonna do is I'm gonna put this in mils for you guys since I'm having a hard time writing today. So half a watt. That's not too much, right? It's not too bad.
I got 0.364.
Okay, take
Milliwatt.
72.77. Oh, you're using that equation you have?
I got 0.727.
So use points. Okay, take 72.77 mils and multiply that by 6.859.
So that's the power at the inductor only,
That's correct, yes.
not through the whole circuit.
That's correct. And if you wanted to find the total power of the circuit, you would have to find the power of R1, and then you use the radical square, the square root of power of X about 1 plus power of X about.
All right, I got it.
Got it?
For for the 4.99, you put 4.99 milliamps, not milliwatts or watts, I should say.
Good catch. I'll see if anybody was paying attention. Sorry. Okay. So just I'm gonna put 43. We have 43.303. Okay, we got the tangents on that. I'm going to get rid of this guy so I can show you something here. I just had something go like boom in my house. I'm not sure what it was. Okay. I'm going to take a break here so I can check it. All right, so if we wanted to find power total on this, first of all, we need to find the power through PR1, but you would do is use this equation. We have to use that equation. So power through PR1, I'll give that to you guys since we'll take a break here in a second. I just had I was looking at it, I was like, what did I do? Okay, this gives me half a watt. So this gives me PR1 is 0.529 squared plus, and this is the radical, by the way, 0.49. So what do we get when we take those two numbers? Somebody give me those. 0.529 square it plus 0.499 square it. What do you get?
I got a 72.72 milliwatts.
Okay. We get that?
Yeah, and again, you can get that same place by adding them in times 707.
Mhm.
Okay.
0.727.
0.727. Yep. Many ways to get to the problem. You're doing it on the using the graphical method on it. So just okay. Any questions on this? I'm going to run the simulator and then we're going to take a break because I want to check to see what I heard a boom over here. I want to see and make sure it's nothing that popped, something that flew off because of the wind. So let's do the simulator. I got to erase the screen here. Is that good for everybody? Okay. I'm just going to clear the screen here. Actually, I'm going to see if I can save this. Cool. I don't even know where the folder's at, but that's okay. I'm going to clear it now. Okay, go back to my mouse. These are the currents. My oscilloscope's up on the top here, so I'm just moving things around. Just if you're wondering what I'm doing, I'm just moving things around. All right, so, okay, I'm going to go run this. So we get 72, I think our current was about 73 mils or something around there. Okay, and I'm going to go ahead and let's put up this. See, I'm getting a broken screen here with this. That is strange. I'm just having the same problem as before, and I'm going to do something, see if we get it. Whoops, Control Z. Okay, I know where it's connected. Okay, all right, there we go. Boom, boom, get rid of that. I just got to reset the circuit up over here just real quick. I'm seeing if we are having a problem with my multisim because of the license issue. That's my question right now. If it is, then we'll build the circuit, by the way. We're going to build the circuit. Yeah, it's working now. Woohoo. All right, so put that on, setup. There we go. I'm going to make these voltages the same. So I'm just going to circle this. So this one and this one are going to be at the same level. I'm going to try to get them both at the same level. That's just me messing with this right here. That's a 10. There's a 10. Okay, so I'm going to move these positions so you can see it. So blue is my output. As you can see, if I line these guys right up, okay, you see that the inductor voltage is leading the source voltage. Perfect. And let's see what our phase angle is. I don't know if I'm going to be able to get phase on here. Probably not going to be able to get phase on here. I'll just go peak, see if I get a minimum. I'm just going to go max. So 14.1. Okay, so I don't think I can get the phase angle on here at all, but let me see if I can. There's a description box, by the way, to see how close we were. I'm looking at the description box right now. That tells me delta T over T times 360. Okay. I'm going to write down an equation here. Delta T over T, 360 degrees. Okay, so we're back onto this. So basically, the delta T to a T, I'm going to have to look at that, but we're going to do it on the oscilloscope, and I was hoping we could do it on here. The utility, no, because I'm not familiar how to use this guy for the phase angle, but I can show you on the oscilloscope on it. So, because if I do measure, I can only do those three things: voltage. I'm going to do channel 2. I could do max, rise time, fall time, pulse width, negative width. So just FYI too. That's why I'm looking at different things right now on this, but let's just keep it at max. Okay. So let's see what else we have here. Let's check power. There we go. Appearance. So what do we come up with the power about on it? I'm going to reset the power on it. It's flipping back and forth. What was our power?
Total power was 0.727 watt.
0.727 watts. Okay, so this is giving me, oh, I'm an RMS. I'm an RMS here. So that's why. Well, are we in RMS? We should be in all of values. We should be RMS too, right?
Yeah.
Okay, so why are we getting a little bit off on that? That's peak average. Unless the probe should be more stable than that. Let me get a power meter. I'm going to get a power meter on this to see what's going on. So power meter's on my right side. On my right side here, should be a watt meter. So I'm going to see what's cooking with this. So the first thing I'm going to do is voltage. So the voltage is going to be, I'm going to do current first on this. So that's going to be that guy. So I can have some place to hook up. And then my voltage is going to cross it. Let's see if we get what we get on that. I must have hooked up something wrong. Power factor. Take a look at what I did with my leads. current, no voltage. Oh, I see what I did wrong. Redo this. So my voltage is going across the inductor. Do I have it right? Go across it. Making things a little easier. It's going to give me a negative value. Well, it shouldn't be giving me a negative, but let's get that. There's my current, and this is my voltage. So I want my voltage to go across it. There's that one. So let's see if we get. Well, isn't that interesting? I must not have something hooked up, but we're going to assume our values are correct. I'll look at this while you take a break here. Whoops. All right, is there any questions on the first series circuit we did? We're just going to take a small break. I'm going to build the circuit over here. We're going to come in and use my equipment. Good to go? Okay, thank you. Let's take a little break. I'm going to go ahead and stop the share on this. We're going to go ahead and switch over to my other guy, my clone, I call him. A host, yes. Okay. Share screen. Okay. First of all, I'm going to show you the circuit that's built. And I know that we used a 10 volts RMS. We're going to say that was 10 volts peak. Just go with me on it. I'm just going to go with the 10 volts peak on it because my function generator cannot go up to 14.14. But the next circuit we do, we'll make sure that we're at peak, and we'll make sure that we can get to where we're at on it. All right, so there's the circuit. What do we come up with for the voltages on the inductor? What was the voltage on the inductor? How much voltage did we calculate on it? Did it come out to be, what was the voltages? 6.858, okay. 6.858, and the other one was about 6.5858, right? Was that correct, both of them? So, all right, so what we came up with on this practical circuit is, let's see what we're getting. Let's see our resistor value first. I'm curious to see where resistor. Right now I have 1.5. Do we have used 1.5 kHz on a single? Is that correct?
Wait, what?
Did we use, what was our frequency on our circuit?
It was 1.5K.
Okay, 1.5K. And then our voltage was about 10 volts, and we had an RMS, but I'm going to say it was a peak. Is that correct?
Yes.
Okay. So if we just use everything at values, I'm going to check my ohms on my resistor to see what it is, just to see why we're off a little bit, but we're close to our values. So I'm going to do is silence that guy for a second, and I'm going to disconnect him. I'm disconnected part of the circuit. I'm going to see my ohms is on my resistor. Okay, my ohms and resistor is 99.28. And I can't do anything about the inductor. I do believe, I'm thinking this is 10 millihenry. Inductor is off. So let's just, we use a 10 millihenry, is that correct on the circuit? It's 10? All right, so if I go back and turn this guy on, turn that guy back on, turn that guy on. I'm gonna ground one of these. I'm just hooking everything back up because everything keeps moving around here. Keep pushing out on it. Okay. So right now I got 5.12 measured across the inductor. Let's see what we get for the, this is what I'm seeing on my scope. Let me see if I can bring it in a little better for you. It does not like that, does it, too much? See if I get some light on it. I tried to put some light on it. Try one more time to see if it goes into focus. Nope. I'm gonna get a light. Well, that did partially work. Just trying to get it in, trying to get so you can see it. Don't know why it doesn't want to go focus on me. Okay. Might just bring that up on a stool one of these days just to see if it works. But you see it gets about 5.12. You saw that with that. See how it goes focus right there? It says 5.12. Okay. So let's take a look. And we can actually calculate this out too so you can see it. Let me get you a voltage reading. I'm just going to get you a voltage reading using meter too. We'll see about the meter in a second here. Let's do the inductor. Let's do this resistor. Let's see how much voltage we're getting across the resistor. And I'm going to do is I'm going to try something. I just want to try something and see if it works. Bring some things down. I'm trying to bring it down so it's focused right at the level we need. Okay. Trying all the tools here so we can get this thing in. Oh, we're almost there. Okay. Try my best here. Better than nothing. You see a little better on that 5.12. See a little better on that. Well, that looks pretty good. Okay, let's check the voltage across the inductor, across the resistor. We should get about the same voltage, about 5.2. We get about 6.858, right? On that. And that means our inductor is different. That means that the inductor I'm using is a 10 mil, but that means that it's not a 10 mil. So we could actually calculate the X of L on that using this voltage, but it comes close. So if I want to do math on here, what I do is I hit measure, and then I'm going to hit math, and then I'm just going to keep it as a peak, a maximum right there. So I'm going to hit the math. And if I take channel 1 from channel 2, and I do that, and I get, there it is, 5.12. So it's about the same. You see it has about 5.12 on it. So that gives it. And then you should also see that we have a phase angle difference between the two on here. So if you notice that there's a phase angle, you notice that the inductor is leading the source voltage on here. You see that as well too. Our phase angle is coming up to be, and this is, I'm going to switch it out between, I'm going to switch it out to see if we get it. Measure channel 2. I just wanted to make sure that my phase angle is not looking for phase angle. I'm going to try something here. Channel 2 math. Same thing. Okay. So we're getting about a 39-degree phase angle, and what did we calculate? What about a 60, a 45, somewhere around there, a 43? 43, right? 43. So this is just giving us about it's about 40. So we're off about 3 degrees. Not too bad. It's not bad. So the reason it's giving me a negative on there is because of the way I took channel 2 from channel 1. Sorry, but that's the only reason why it's giving me a negative on it. Let's see what else we want on there. But that's what the circuit looks like. That definitely looks like it. Now I'm going to show you something else. This is pretty cool. So if I actually do utility, give me a utility display, and I want to do is look at the phase angle. There's another way to actually to do the calculation on here for the phase angle, but this is actually telling me there is a phase angle on it. And if I clear up this screen a little bit here, and I'm just going to walk you through this. If I actually take the value from this point, and let's see, and from here, way out here, and we have to keep our voltage the same, so we'll take it from here to here, and then from here to here, we can actually calculate it. And this is using a French terminology. I can't remember the name of it. It's Lahirst or something like that. But that's another way of actually calculating. If this line was straight across, if there was a straight across line across here, just a straight line, we would be at 45 degrees. We would be at 45 degrees. What's interesting is that even though I'm not getting exact values because it's 10 millihenry is way off. Can I try another 10 millihenry? Sure, I could try another 10 to see if we actually get anything closer. I got another 33. Looking to see kind of stuff I have at 47. It's not going to work. 286s. All right, I don't have another 10 mil, but if we did, we could swap it out and see if it gets us any closer. So, is this helping you guys a little bit? Okay.
Yeah.
All right. Let me just go back to the display here. There she is. So, let me just do the math on here. See, the math allows us to, and I could get rid of channel 1 here. And I just put up channel 2. You can see that the math here is about 5.12, which is the same, close to it. The problem is our inductors are not this, is not perfect. I bet you this 10 millihenry is either way off. Not much I could do about that. I could actually figure the ohms out using Ohm's law, 5.12, but we're probably going to get really strange answers on that. Current-wise, do you want to see current or measure circuit? Okay, let's do that. Okay, I'm going to bring this meter up. I got wires that are coming off the board here too. Remember, our resistor was 99.2 something, so it wasn't 100. And our inductor's probably way off too. So just give you a heads up on that. So, all right. So there's our circuit. I'm going to bring this guy down a little bit so you can see him. Be nice if things just focused in really good on us. Okay, so I'm going to switch my meter over to AC. I'm going to break the circuit. Okay. So I'm just disconnecting wires here. That's all I'm doing. Putting things in parallel, putting things in series. So here's my function generator. That goes to my meter. And then I'm going to do is I'm just going to hold this black lead. Actually, let me get the polarity correct. So we're not doing anything here. Let's see. I want to do that way. Going in, going in, going in. I was right. Going in. Yeah, I was correct. Okay. What did we come up with the current on it? What was it before? Mills. Frequency. I'm just making sure everything's connected up, right? 1700. Frequency. Okay, here we go. I just want to make sure I'm getting everything back on the screen here. All right, I'm not. Oh, it came off again. I was wondering why we're not getting anything. This guy keeps popping off. Let's try that again. Okay. There we go. Okay, so we got 35.43. Take that times that by 1.414. What do we get? $40.53, is that correct? And what do we calculate for a current? 43 point something?
You said 35.46 times what?
1.414? We calculated what, about 43 mils or something like that?
14.6?
I thought we had 72.77.
72.7? Okay. Something come off. 72.7. Where am I off? Okay, this is 35.3. 10 volts peak. Okay, 10 volts peak. We're going to say it's 10 volts peak. What did I do wrong? No, that's right. Times it by 2. 73. You get 73.8 or something like that. Is that correct? Okay, we're on an RMS value on this. So I just want to make sure my numbers are writing on it. So 35.5. We have 10 volts peak. Okay, so we had half of it. So I got half of my current. Trying to figure out why we got half the current here. Okay. Got the voltages up correct. 5.042. Come on, think through this. 35.5. There's 40, and you said we came up with what, 78 or 73.78?
72.77.
Okay. Why are we off? That's RMS to peak. Couldn't have been a peak to peak. Did I mess up someplace? All right, hold on. You know what I did mess up? I did mess up. I think I did mess up. Hold on. This could have proved that I messed up someplace. Unless I was correct. No, V total over Z total. And our V total was what, 10 volts? Is that correct? Give me the 10, was it 10 volts divided into our Z total? What was our Z total?
One 137.414, but that would give us 72.77 milli, which is what the I total was.
Okay, 72 points, 72 point, okay. And then why are we only at that? I think I know why. I think I know why. Give me 1 second. Remember I told you about circuit loading? What did I forget to do? Yep, I forgot to do about my circuit loading. Let's check circuit loading real quick here. Oh. I bet you we're not even close to that 10 volts. I'm going to go
Charles,
ahead.
didn't you say that in order for your signal generator to put out 10 volts RMS, it would have to put out 14 volts peak, and that it can't go that high?
That's correct, yes. But I think we,
Okay.
can we assume that, could we assume the circuit was at 10 volts peak? And all our values were peak values? Could we assume that?
Well,
I think we can.
Your drawing was 10 RMS.
Volts RMS, right. So it's 10 RMS. So let me check the circuit loading, and I think there's two parts to the issue. We're gonna do another circuit just to clarify everything up, so we'll get rid of, so we get everything cleared up here on this. Let me check the circuit RMS. Let me check the voltage. So peak to peak, channel 1 peak to peak, I got 20.4. That's pretty good for a load up. That's why it's not loaded. Yep, there's the problem. We're at 16.4. So I don't think I'd go up any higher. Yep. So we're only at 16.4 volts. There's the reason we're off by 4 volts. If we add the 4 volts to it, our current would be up there. Let's do another circuit. How about if we do another circuit exactly with the function generator so it's perfect? How's that? Does that sound good? Okay. We'll do another series. So next week we'll pick up parallel, and then we'll move on. Sounds good to us. Is it good to you? Okay. So let me go back to stop share here. And let's do this. I'm going to go back to myself. Yes. Okay. So I should be back. Let's build this circuit. And I think we can use a second one. Do you want to use 2 inductors, or do you want to use 1 inductor? 2 or 1? Put it on your thing. Or just you want to just do another inductor, 1 series without it. Okay, let's do let's do another circuit this time. Let's go back to multi-sim. Let's design up our circuit here. Okay, so if I do that and I'm going to go ahead and use a 33 millihenry inductor this time. So you should have a second circuit, but to go ahead and draw this out, this is what we're going to do. And instead of 10 volts, we're going to use not RMS. We're going to change that out to, I'm going to change that out to a power source. AC power. Let's see if it allows me. No, I don't want that. Let's do single voltage source, AC voltage source. That's what I want. Okay, so I'm going to do that. Close, close, close. Peak, There we go. That's what I want. So now we're going to do everything in peak form, and I'm going to change that 1 volt peak to something else. So what we're going to do is go with 5 volts peak. That's a peak value. And I'm going to say we're going to need get rid of this 10 mil, and we're going to go with 33 mil. And I'm going to calculate out the decibels real quick, just make sure I'm good on that. Instead of 1500 volt, we're going to use 1 peak. I'm just making things up as I go here. Get rid of that. Boom. 1 kHz. Just give me a second. We're going to make this. That's good enough for me. Okay, so we're going to make that 500 hertz, 5 volts peak. So everything's 5 volts peak. My function generator, 5 volts peak. Perfect. Okay, so that's a circuit. Same thing, just doing this. I'm going to make this a standard circuit so you can see it. I hope that just gets there. Okay, just delete that. Just do that. Okay, these are the values we're going to do. 133 mils. Everybody good on that? Okay, that's our circuit. So that means I could put my function generator 5 volts peak. I could put my 500 hertz in there. Should be good. So let's find decibel 1. Let's find decibel 1 first. So everybody give me decibel 1. Somebody give me decibel 1.
One oh 103.67.
Okay. Check each other's work. Put it in the chat if you get something else different. 6.7. I'm going to say 6.73. I'm going out 3 decimals. Just go out 3. Is that good?
I got 103.67.
That's good. You guys can keep that. That's fine. Okay. Let's decibel 1. Okay, so it's 103.67. All right, so we have that. Let's find Z total. Let's do Z total. Somebody give me the values Z total. Do we have Brett still here? Who's here? Who's here? Who's here? Who's here? Yeah, Brett. Brett or Daniel or somebody go ahead and give me Z total. So that'd be R1 squared plus XL1 squared.
Is it 144.04?
Okay, got that answer.
I got 144.04.
144.04. Okay. Is anybody disagreeing with what we're doing here? I'm just going to go out 3 decimal places just to get some accuracy on this, that's all. But you guys are correct. If there was an answer that was wrong, I'll let you know. Okay, let's do V. Exabel 1. Actually, we have to find iTotal first. Let's do iTotal first. Pushing this. iTotal first. And you could do so it's 5 volts peak. Go ahead and give me the answer.
I got 34.71.
$34.71. Does everybody get that? Okay. Let's do V Exabel 1 and VR. What's the equation we're going to use?
For VXL1,
Yeah, what's the equation would you want to use?
iTotal times R1.
Okay. Okay. What'd you get? You get 3.47 volts, something around there.
What? 3.471 volts?
Yep. Did you get that?
Yes.
And what'd you get for the second one? Is it something like 3.5? See if
It's
I'm
also
correct.
3.47.
You got 3.47 for Exabel 1, and did you get 3.59? What was that, Jim?
I got a 3.4712 for the VR1.
Yeah, 3.471 for VR and 3.598 for VXL.
Okay, I mixed it up. Yep, I got you. I mixed it up. Okay. Okay, so I mixed it up. So VR1, 3.471, right? Okay, 3.471. And the other one's 3.59, right?
Yeah, 3.598.
Yeah, I mixed it up. I just realized that up here I drew it up the wrong way. All right, so those two, what'd you get for phase angle? Theta?
Isn't VR1 3.598?
VR1 is 3.47. 100 times it by 100 ohms times it by 34.71. Gives you 3.471. And VXabel is 103.67.
Oh, all right.
Let me make sure that one is correct. 3.59. Yeah, right. Okay. So this one is going to be Xabel 3.59 divided into 3.47. What'd you get for the phase angle?
46.03.
45 point what?
46.032.
Okay, 46.032. What'd you come up with, Jeff?
Yeah, same.
46.352 degrees. Sorry, my hand's a little shaky right now. I'm going to erase that. Is that what you got? 46.352? Thanks, you guys. Appreciate it. Okay. Any questions on that? You good? Ready to build? By the way, I was putting the circuit together here. Okay. So let's do it. Let's get this out of the way. Show you. Right now, what we have to do is first thing that I'm going to do is put the components in, set the voltage up on the function generator. I'm going to adjust the function generator so I get 5 volts peak out. That's what I have here, 5 volts peak. So I have to get that function generator up to 5 volts peak. Let's do this. All right. So let's mouse over. Stop share. Actually, we could run it over here, but we're going to build the circuit. This is stop the share. I'm going to switch over to my clone. Okay. Okay, the first thing I'm going to do is I'm going to look at my circuit, and I'm going to bring this guy So the first thing I want to do is I want to load the circuit up to see if we have. And we have what, 500 hertz? It was a 500 hertz on it, right? 500 hertz?
Yep.
Okay. All right. So frequency 500, enter. Whoops, that's 500K. There we go, 500 hertz. And let's see, we got peak to peak is 8.6. I'm just going to bring it up to 10 so I get a 5 volt peak. Is that good with you guys? So I'm going to go over to my function generator, and I'm going to bring this number up 8.6. So you see the 8.6. So it goes up to 10. I hit the wrong button. There we go. I'm going to do is bring my cursor over 1 bit. And I'm going to bring this up till just like that. Okay. It's 10 volts. Okay. So I'm going to go measure channel 1, and I'm just going to get, it should be a maximum on that. So I get 5.2. I'm getting a little, oh, there it is, 5.0. It's good enough. It's floating, but it's okay. Let me see what I get a measure on a peak to peak on channel 1. $10, 5.2, 10.2. I'm floating, but it's okay. It's okay. So I'm going to do is bring these guys up to, I'm going to hit auto reset. There we go. All right. I'm going to bring this guy up. Hit the measure. Channel 2, channel 1. I'm going to get rid of peak to peak. Measure. Okay. Okay. So we have 3.04 on the inductor. That means my inductor's still off a little bit, right? Breathe me on it. Okay, so I could bring that down. Right now, my function generator is almost at 6 volts. It's quite a bit. So 500 hertz, 3.04. What do we get for voltage across the inductor? Give me the voltage. What was the voltage across the inductor? 3.14, I think it was. 3.4.
3.598.
3.598. Thank you. Okay. And we got 3.04, not too bad. That's because my inductor's not at that value, plus my resistor is off too. So my Z total is going to be off just a little bit. So being off by, what is it, half a volt is not too bad. Better than what it was before. Let's check current. Let's check current on this thing. I'm just going to bring this back up so I can do current. So this is an RMS value. I'm going to have to get something to clean that lens off, I think. Maybe it's not. Maybe it's focus. It's just light issue. So give me 18.33 times it by 1.414. That gives us a peak, right? What was the total current we came up with the circuit? Please be close. What was the total current that we came up with? Was it about 31 point something?
34.71 milliamps.
34.71. Okay, thank you. 71 milliamps. Okay. So let's see. I'm just curiosity. This is bothering me a little bit. So right now, I'm coming up with 18.34 1.414. I'm going to use my meter to see if I get an actual, what I'm getting an actual peak value on this. I'm curious. So I get 25, 26. So I'm off almost 8 mils. That's a little high. I want to see what on my meter's metering because that scope, I'm assuming the scope is good, but let's just check it. Let's just check it to see what's going on here. But again, remember my inductor is probably not, my inductor is not at that 33 millihenry, right? Is not. It could be anywhere. It could be anywhere on that. So let's just check. I'm just curious to see what's going on. I'm using 2 meters to see what's going on in my circuit. So my circuit's back. I've set my meter for mils, for AC voltage, and I'm just going to go across it. 3.41. 3.41. So I'm looking for 5 volts. I'm going to get some leads on here so I can actually look at this a little better. This is called loaded. So you're going to see that 1 meter is going to give you, one device is going to give you some one value, and another device is going to give you another value. Let's get another lead here. There we go. So I'm checking. Because remember, the scope was bouncing a little bit there too. So let's check. So I got 3.14. 3.41, 36 times by 1.414. I get 4.8. So if I bring the scope back up just a little bit, maybe that'll affect our total current. We could see that. Let's see. I'm going to bring it up. I'm just going to bring it up to 4.9. That gives me 5.07. That's close. That's closer, right? And if I look at my scope, right now it's telling me I have a 5.4 maximum. So my meter's telling me I got a 5.07. The scope is telling me I have a 5.4. Which one's right? This is where I'm trying to show you that there's differences between the meters, the different test instruments. So if I do that, and now I measure current, and I decide to measure current without blowing up my meters here. Went up a little bit. Didn't get it up all the way, but it went up a little better. We were not 25, or what we were before, somewhere around 26. This went up to 27. So not too bad. But you can see that what's causing this problem is that I bet you the inductor is not at 33 mils. I bet you the inductor's maybe at 30. That inductor's probably at 30. But it does give us a good idea how to do some of the readings. We see that there's a phase change. We see all this. How would we get exactly the components we want? Precision. Precision. Does this help? Okay. I'm going to stop the share here. Okay. All right. So a series circuit, if we had a double inductor on it, you would just have to add the exabalance together. Do you want to do one of those right now? Or do you want to call it for today? So right now it's 1210. And do another one. Let's get a thumbs up if you want to do another circuit. Nobody's giving me a thumbs up. There we go. Okay. Daniel? Brett and Drake. Are you there still?
Yep, I'm here. Personally, I think I'm good.
You're good? Okay. I'm going to go ahead and do one more. If you wish to bounce out, there's homework on this. On the series, do only the series part of the problems. Next week, we're going to do parallel. And then we're going to move into, I am thinking right now, I want to know your opinion through an email. And I do have a poll, by the way, before anybody bounces out of here. I'm going to drop the poll in, so if anybody wants to stay on, you can. But I'm going to do the poll right now. But I'm thinking of combining test 3 and test 4. I'm thinking about it. So we're cutting back on the tests. If you like that idea, or if you don't like that idea, send me an email. But I think it'll be good because we could just chug through this and add some more time to our stuff. Does that sound good to you guys?
All right.
I'm going to go ahead and shut down this guy. I got to shut down one of these computers right here to be meeting. Okay, that was me going bye-bye because I want to do. This is for those who are still doesn't want me to go. I'll get it back up and running in a second here. Okay, let's do this. Try the poll again. It's because I had another computer up and running. It doesn't like me. So, all right, I will send a poll by email, and you do the poll by email. We're going to do another circuit with a with the double inductor. And if we want to, I could go back to the other computer and we could turn it on, or I could use the camera to point down on it. So there's a couple options I could do here for that. So instead of just using the document camera, so I could probably pull away from that for a little bit. All right, let's set up the circuit. Real quick here, let's set up a circuit, and that'll be your second one. That'll be an inductor, and I'm going to put this up on the screen. Your screen. So that's that one. There we go. So you should have something that looks like that. Does everybody have a PDF on that one?
Weren't we just doing this one?
What's that?
Weren't we just doing this one?
No, this one's a double inductor, 33 and a 10. We have a 33 and a 10. Can you see that? Whoops.
Oh.
Can you see that? The circuit? Okay.
Yeah, I can see it.
All right. And then I'm going to get rid of this source. So I'm going to get rid of that source, get rid of that. And I'm going to put my own source in because I don't like that AC voltage. Boom. I didn't like the one they were using. I'm going to go with, actually, I'm going to go with 5 volts peak, and let's keep it 1K hertz. Let's keep it at 1K hertz. See what happens on that. All right, so first of all, you have 2 inductors. There's 2 ways to do this. You can find Exabel for each one of them, or you could do is combine the Exabel. You could combine the inductors and then find Exabel total. So it's up to you which one you want to do. So if we do it, if we wanted to find these 2 the old-fashioned way, so what we would do is put in L1 plus L2 is equal to L total. Now, we already found Exabel for these guys, so you could already have these numbers. So you could do it both ways. So Exabel 1, Exabel 2 here is going to be equal to, we already found these, so I'll just, maybe we didn't find it from 1K. We did not find it for 1K hertz. We did not. So if you want to do it for this way, if you take these two, 33 plus 10 is 43. That's just adding these two together. And that gives you L total. And that way our Exabel total is going to be equal to 2 pi FL. And I'm going to do is put up the Exabels over here too. So this is going to be Exabel 1. So 2 times pi, 2 times pi, times it by 1,000. Yeah, 1,000 times it by 43. 270.17. See if you come up with this value. Just went out a little bit extra places. I'm going to find these guys, and we'll see if they add up together. Just see what happens here. 7.
Whoa.
What's the whoa?
Oh, never mind. I was looking at the wrong one.
Okay. Scared me a little bit there. I was like, maybe my math is off. Okay, so if we add these two guys together, that better be equal close to 270. And it does. It's very close. It's very close to it. The adding the Exabels give you a better answer, but the nice thing about this, about having these Exabel 1 and Exabel 2, we could actually find the voltage across these two inductors too. We can find these two inductors. So we get 270.1769. I'm going to use that one for my use part of Z total. I'm just going to use Z total for that. So if somebody tell me for Z total, if we take R1 squared plus Exabel total squared, somebody tell me what you get. Let me get the chat back up here.
I got 280.09.
288.09.
Yes.
Do we have an agreement? .0809. I'm going to say 09. Is that what everybody had? Let's do I total.
$17.356.
Okay. I'm assuming that's mils, right?
Yes.
Excellent. It's kind of funny when I start writing like this, my stomach's like yelling at me, food, food, food. And I'm like, no, you're not getting food right now. So 17.356. Okay, let's find the voltage across XBL2 and XBL1. And then I'm going to set this circuit up, and I'll show you what it looks like. I'll actually use my webcam. Be much easier on me. Use the webcam on it. So V XBL1 and V XBL2. I'm not going to put the equations up for this. So you just take your current total and multiply it by your XBL1 and XBL2.
Is that a 19.356?
17. Let me erase it. Let me get it. Let me erase that. I noticed
For
that it was
VR1, I got 1.735.
okay. What was it for a VR1? 1.735?
Yes.
Even though we didn't need that one, we did because that's important. Okay, let's do XBL1 and XBL2. Good job on that. I agree with that. So I'm going to put down, Jeff, what did you get for XBL1 and XBL2?
So for one, I got 3.598.
3.598 volts. And XBL2? Let's do XBL. I'll do XBL2. You guys have been working hard. I'm going to need to do some math.
1.09.
1.09. Is it 162 point? XBL1 is 62? No, it is 62, isn't it? 62. Yeah, it is 62. Okay, 1.09 volts. I can't even read my own handwriting. There we go. Okay. I almost put the wrong one in. Okay, I agree. So now if we wanted to find the voltage total for this, we would have to do is square all those voltages and take the radical of it. And that's the only hard part on that one. All right. Now the phase angle difference on this. Let's take it. Let's just do the resistances. It'll be easier. So we do XBL total divided into Z total. Let's do the phase. It has to be XBL total because I'm doing by the resistances. Plus, it gives me a better accuracy too. Set the circuit up.
I got 69.69.
Okay. Okay, let's see what actually this looks like on the circuit. Let's build the circuit up. So that's my 33. I might go back to the college just to do these measurements and see what we get for the inductors and then use those values. That way we get some closer readings. Okay. All right. how am I going to do this? Okay, I think I could keep that circuit on there. I'm trying something here, folks. Okay. Here's the circuit. Is that bad? So basically, I have my two inductors. Point that. There we go. So my resistor, my two inductors are in series. Get this guy out of there for now. How's that? Is that better? Okay. So my resistors, my function generator now. It's going to move. Oh, right here, it didn't move. So I'm going to set the function generator. Good to go. So that's my circuit. What I want to pay attention to is this right back here. So I'm going to do is make a little stand for this. Hey, stay put. There we go. I might just have to hold this. Sorry, bouncing around a little bit there. Okay, so that's what it looks like so far. So now what I want to do is, I need another hand here. Just keep it right there. Okay, so what I'm going to do is connect up. So I got my function generator up and running. I said it's 1K hertz, is that correct? Yes. 500 volt, 5 volts peak, 1K hertz. Okay. Five volts peak. So we have that. I'm going to put up my meter to see what I have for a loading of it. That wind is strong because I got a lot of noise going on around here at this house.
Same for me.
What's that?
Same for me. The wind's pretty strong today.
You notice the multimeter. It just blew the fuse on this one, but that's okay. Keep doing that. So 3.96. Let's see what we get on that. Right now it's telling me I got 5.08. Can you see that any better? A little bit?
Sort of.
Better off with the document camera, right? Okay, let's just.
It's still a little bit out of focus, Charles.
It is a little bit out of focus. Okay.
Yeah, that's fine. Don't worry about it. Just keep going.
Okay. Okay. So got all that. I'm going to hit auto set. And first of all, I got to do is I got to put down, I'm going to put this, actually, I'm going to take and I'm going to measure across the second one to ground and hit autofocus. I'm going to disconnect the meter. Okay, there she is. Okay, so phase angle. This is just channel 2 to channel 1. That's why the phase angle is off. So don't pay attention to that. Okay, so basically, you see there's a phase angle, but I'm going to go ahead and I'm going to move some stuff around here so you can see what goes on. I'm just going to move some things around here. And we're going to take some measurements. So basically, I'm going to have to use the math function, but I want to see what on this inductor. So I'm going to take this inductor and subtract it from this inductor, and I should get that. Let's see which one we get here on that. So if I take measure 2 to 1, I get 4.04, and that gives me, let's see what voltage is. Look at that. Voltage Xbel 1, that definitely gives me Xbel 1, which is close to the 3.5. This gives me 4.04. Actually, it's a little high. Let's see, did I do that right? Let me make sure my voltage is good on this. So we got 4.04 right now, times about 1.414. That's why I'm a little high. Okay, so I'm going to bring down my voltage, my amplitude. Still too high. I'm using my meter here to give me the exact value on this, because this is a true RMS meter. Still high. That's perfect. It's close enough. So what does see? We get maximum. We got 3.8, and we measured 3.5. So 3.8 to 3.5. That's not bad for Xbel 1. It's not bad at all. And let's see. That's using the math function. Let me just get rid of some of this so you can see what's going on here. So that's that red. So that's that red right there that actually that I'm looking at. So what I did is on this is my probes. Just showing it to you. So this is channel 2. This is channel 1. So what I did is I subtracted channel 2 from channel 1. And that gave me the voltage across Xbel 1 right there. Let's see, current. Let's take a current measurement real quick to see what we have. That's voltage. I'm going to switch it out so we get current. All right, just give me a second to get it on. You see that? That's better. Okay, so that's current. I just noticed something here. Hold on for a second. I got something wrong in my circuit. Grabbed the wrong one. That's gonna make a big difference. I was looking at something. I had it when the inductors was wrong. 3.4. I'm right on the money. Right on the money on that. So that's 3.5. This is now 3. That's right on the money. Okay. I know it's bouncing. Sorry. And we came up with I total of 11.28. Well, this is going to come on close. This is actually much better. I got 16. We came up with what, 17? That's close. That's very close to it. And you can also see on my meter that I have 1K hertz. And this is 11.25. So very close to it. Very, very close. Okay. And just to show you what I mean by the scope. There's a scope. Is that a little better? Is that blurry still? Yeah, okay. But my scope says it's about 3.4, and we had 3.5. So voltage across the inductor is about 1. So very close. Very close to it. All right. Instead of bouncing around all over the place with you guys with that. Any questions on that circuit?
I think we're good.
We're
I
good.
think.
Okay.
Yeah, thank you for doing another one of those.
You're welcome. I know I'm gonna work on. I'll work on the technical stuff. Let me see if the polling will work. Let me see if I got the poll work. It says it's logged in from another device. I don't understand why I'm logged in from another device since I'm not logged in. Okay. I'll send the poll out to you guys, or we'll do it next week. So we agree on the test. Combine test 3 and 4.
Sounds good.
All right. Any questions about the quizzes? I'll have a couple other quizzes on there. Probably wait until we get to the parallel next week. We'll get to the parallel, and then I'll throw one on. I'll make a brand new, fresh copy of a quiz. And what the quiz will include will be a series inductor, a parallel inductor, and then